Hello everyone, this is ML Naruto. Welcome to my channel. Okay, so yesterday we have already discussed about how to run the linear regression model using the stats models library, right? And day before yesterday we have already talked about how to run a linear regression model using the scikit-learn library. So this is a linear regression model using the stats models library. See here the heading, the stats models. So using that, I have provided my entire data by concatenating them together, and then I have got this kind of OLS regression results table. So in that video, I haven't explained what is a kind of table. What is it actually explaining, or what is it actually trying to convey? I haven't explained. Why? Because that's a kind of implementation part. So, and also this is a topic of which is related to hypothesis testing. So I have already thought to explain this particular topic in the next video again. So now this is the time here. So, okay. So in this video, I'll be explaining what are all these things, trying to actually trying to convey us. The most importantly, what is meant by this coefficient and the standard error and the t here and the p values here, and what is meant by this r square adjusted. Yeah, we have already seen what is meant by r square and adjusted r square. So yes, I'm gonna explain all these things today in this video particularly. So if you want to understand this particular table, so before that, I want you to know about something. Just head over. So, okay. So the discussion is about the hypothesis testing. Hypothesis testing. So what is meant by hypothesis testing? So hypothesis testing is a situation where we can decide between two things, right? Between two things. Though what is the first thing here? The first thing is H naught, and the second thing is H1. So what is this H naught and H1? So if you look at here, H naught is actually saying that there is no relation between our independent and dependent variables. Okay. And if you look at this particular H1, and this is saying there is some relation. Okay. There is some kind of relation between our independent and dependent variable. So in this hypothesis testing, we'll be facing two situations here. The first one is the hypothesis, the null hypothesis, where we can also call it as H naught, right? So this H naught is nothing but the null hypothesis here. So this is, so I'll be using a different color. Maybe red would be the best here. So this is the null hypothesis, right? And this is the alternative hypothesis. Alternative hypothesis, right? So these are the two situations where we usually find, right, while dealing linear regression. So here, what is it actually saying? It is saying that there is no relation between our independent and dependent variable. And here, our alternative hypothesis is saying there is some kind of relation always between our independent and dependent variable. And imagine that this entire platform is a court, and uh, we are some kind of we are the lawyers here. So we need to prove something. For example, what are you interested in? So if you are interested in null hypothesis, you need to prove that this null alternative, if you are interested in this alternative hypothesis, you need to prove that alternative hypothesis is true. Or if you are interested in null hypothesis, you need to prove that null hypothesis is false actually. But in general, what should be the case is, in general, the scenario would be alternate. We always want to prove that alternative hypothesis is actually the true, right? We always wanted to prove this alternative hypothesis is true. So if you want me to discuss about that, so for example, see here, I'll tell you. Okay, so here I'll be having some kind of a graph here. Okay, so actually, so this is the x-axis, okay, and this is our y-axis. And what is this here? So from here is x-axis, right? So what is the half of x-axis? Nothing but the x bar. That is our mean. And what is the mean of the y here? Nothing but the middle value of the y. That is nothing but the y bar here, right? So, okay. Okay, let's imagine we have two variables. One is our independent variable x, and one is our dependent variable y. And let's imagine these two variables don't have any kind of relationship. So these don't have any relationship, no relation. I'm assuming this, right? If I am assuming this, there is no relationship between these two, then the data points, if I want to plot them on a plot, the data points would be like this. Okay, so if I want to plot the relation between these two, the obvious shape would be like this. Why? Because see here, I'm assuming like this. I'm assuming that there is no relationship at all between these two variables. So due to that reason, I'm I'm having this shape. I mean, I'm experiencing this particular shape when I plot all the data points on a scatter plot. Okay, so this would be the 2D view, the two-dimensional view. Okay, this would be the two-dimensional view here. Okay, so so this is a 2D two-dimensional view, right? So if you want to experience this entire plot on a three-dimensional view, so how would be that? For example, see, so this is the data, right? So this is the data, and so this is the data. This is not the three-dimensional view. I'll be drawing the three-dimensional view in few more minutes, but just have a look at here. So what I'm trying to say is, these are the data points. When you plot the data, so the usual shape of the data would be like this. It will form a bell curve here, right? And this would be our mean here. This would be the mean here. Mean is nothing but the, what is the mean here? That's the central value, right? So here lies the density of our data points. Density of data points. Density of the data points is very high. Where? At the center of the data, the density of all the data points would be very high. And if you look at here, that is the far away from the central value, that is, if the data points are lying far away from the mean, the density would be very low. Here also, the data points are actually lying very far from the central value. Then we can say we can observe that density of the data points are actually very low here. But when the data points are actually lying exactly at the center, the density would be very high. Why? Because see, just observe the graph here. Here we have, you can observe more data points around the center, right? Around the center, nothing but the mean here. But when you look at the data points that are away from the center, the density is somewhat low when compared, right? So this is the two-dimensional view. So here the thing is, let's assume if I'm assuming that if H naught is equal to true, that is, if my null hypothesis is true, then I want to know what is the probability of finding the coefficients in this particular sample which is drawn from the universe, right? So for example, this is the population data. Let's imagine this is the population data. Okay, so from this particular population, I have drawn some kind of sample here, right? This is the sample data. I have taken this sample. So that sample is nothing but this particular graph here, right? So this sample is nothing but this particular graph. So I have taken some sample and I have plotted on a scatter plot. And now I'm assuming that if my null hypothesis is true, that is, null hypothesis, what is meant by this null hypothesis? There is no relation between independent and dependent variable. That is this thing. I'm saying that there is no relationship between x and y. That is, our null hypothesis is true. Then what is the of finding probability of finding the coefficients coefficients in the sample if the sample is drawn from the universe. If they're drawn from the universe, where H naught is equal to true. Okay, so what is the probability here of the coefficients? So I just want to know here, I just want to find out this thing. So what is it? So did you get the point here? See, I'm for example, see here, this particular thing, that is, this is my this thing is our population here. This is the population data. Okay, this is the population here, and here this is the population data, and out of this population data, I'm extracting some kind of data, small data, which is nothing but our sample here. When I plot the sample on a scatter plot, I have observed some kind of there is no relationship among x and y here. So that means what is the H naught here? No relation between independent and dependent variables. So that means we can confidently say that if H naught is true, that is, if let's assume if null hypothesis is true, then we want to know what is the probability of finding the coefficients in that sample where our sample is actually drawn from this universe, right? So what is the probability of finding the coefficients in this sample here? So that probability is nothing but, so that probability is actually nothing but these p-values here, these p-values, all the p-values, right? So that probability of finding the coefficients in our sample is nothing but these p-values here. So that's the purpose of having these p-values in our OLS regression results table here, right? So that's the thing here. And now what I can do is, you have got to know that this is the two-dimensional view of our data. So so if I want to plot the particular thing on a three-dimensional thing, so what can I do here? So I would be plotting this. So this is my density here, and this would be my x-axis here, and this would be my y-axis here, right? So if I want to plot, so what would be the mean of the y here? So the central value, that is this particular line, would be the mean of y here, y bar. And what would be the mean of x here? So this particular line would be the mean of x, that is x bar. So when I try to plot this particular that earlier plot in a three-dimensional format, so what would be the imaginary graph here, like this? See here, this would be the three-dimensional uh, plot of our data. So around the mean value, all our data points will actually be lying around the mean value here, right? See here, the data would be like this. All the data points that are actually lying far away from the mean, that is the central values, are of low density, and the data points that are actually lying closer to the central value are of higher density, right? So what is this density here? So the density here is nothing but the number of data points per unit area. So that's the one of the kind of axis here. And now when you observe this particular plot here in three-dimensional, it looks like a bell curve. First observation is it looks like a bell curve, right? So this bell curve is in the shape of a H naught. Why? Because we have already assumed that there is no relationship between the dependent and independent variable. That means you can call it as H naught is true here. That is, null hypothesis is true, and our this particular sample has been drawn from our population, that is this is our population, right? From this particular sample has been drawn to this here, right? So this is the three-dimensional format. And now okay, in the same way, can we plot the same three-dimensional plot for our previous data which we have already worked on, and on which we have already implemented our linear regression? earlier, yesterday. So can we plot that? Yes. How to do that? Just have a look. See, in the same way, I'm just plotting the three dimensions here. That is the one axis would be our uh, the dependent variable, that is the mpg, that is the miles per gallon here, and the other dimension would be our the one of the independent variables, that is horsepower. Okay, we want to know what is the relationship between the horsepower and the mpg here. So just have a look at here. Where is it? The horsepower. Okay, so here it is saying the horsepower is actually, the coefficient of the horsepower is minus 0.0392. That means it is having some negative correlation, right? So it is not a positive, unlikely to the positive correlation, where if horsepower increases, mpg will also increases. But here in this case, horsepower will decrease, right? Horsepower will decrease, and mpg, if horsepower decreases, then mpg increases, right? Miles per gallon increases. So this is the strong negative correlation here. So see here, if I want to plot this particular thing on a graph, so how can I plot the negative correlation here? So the data points would be like this. Right. So what is the x bar here? So if this hp is nothing but a x means, then this would be the x bar. What is the y bar here? If mpg is y means, then this would be the y bar here. Right. So this is the y bar, this is the x bar. That is the mean here. So this above correlation is in the three-dimensional forms, right? It is so when you look at here, so what is the shape of this particular thing? That is, when you look at here, what is the shape here? What is the shape? When I try to form this particular shape separately, the shape would be like this. See, the shape would be like this, right? So this would be the shape here. So this shape is nothing but a flattened bell curve. Okay, this is a flat bell curve, you can call. This indicates that there is some kind of correlation between the two variables, right? We are clearly, I mean, we clearly knows that by just looking at the shape of this particular data, we can clearly say that this is having some strong negative correlation. Why? Because if if horsepower is actually decreasing, then miles per gallon will definitely increase. So this is what it's actually, uh, by this graph we are actually knowing that this, if this hp, that is horsepower column, and the miles per gallon is having some kind of a strong negative correlation here. Okay, so now I want to know what is the probability of finding the above correlation between the horsepower and the mpg in our sample here. So what is the probability? I want to know what is the probability of finding coefficients coefficients in the above sample, which is from the which is from the universe here, right? For example, this, let's imagine that this is a sample here. This is the sample data. This sample data is nothing but the shape of this particular data, this data, right? So this data, this particular shape, see, did you just see here? This is the shape which I have drawn separately, right? So this is nothing but our sample data. And where is our population data? When you ask this question, our population data would be here somewhere. So this is our population data, nothing but the universe data. We can also call it as universe. So after finding this, that this is having some negative correlation, I want to know what is the probability of finding the coefficients in the above sample which is drawn from the universe. So I want to know whether this data, uh, I mean whether this particular population is having the coefficients or not. I want to know. So for that, what we can do is we need to rely upon the p values here. So we just want to look for the p values. So the rule for the p value should be, if the p value is 0.05, then reject null hypothesis. Sorry, reject null hypothesis here, right? With 95% confidence interval. 95% confidence interval. So we can confidently say that if p-value is less than 0.05, we can definitely reject null hypothesis here, right? But what if we have another situation, like we have p-value here which is greater than 0.05, then we fail to reject a null hypothesis. That is, we don't have enough evidence to reject the null hypothesis. So ultimately we accept the null hypothesis, right? So even if we say that we accept the null hypothesis, we should not say the term. We should only use we failed to reject null hypothesis. Okay, you will never say we accept alternative hypothesis. You should never say that. You only say this term. We failed to reject hypothesis. The reason maybe a few statisticians maybe they won't agree for that term. Even I too don't know the reason. Why is it like so? So yeah, in the ideal situation, maybe you should need to. You should pronounce it as we failed to reject the null hypothesis, right? So just have a look at here. Uh, just go to the our coefficients table here. So when you look at what is the p-value here, p-value for the horsepower, we are actually observing, we have drawn the graph between the horsepower and the mpg, right? So if this is the horsepower here, so where is my p-value here? So this is my p-value, 0.016. So p-value is equal to 0.016 here, and that implies p-value is less than 0.05, right? So this value is less than 0.05. Then we can say that, then what we can say, we are actually rejecting null hypothesis here. We're rejecting null hypothesis. So just go back here again. See here. Uh, See here. What do we have? What we have said? Our p-value is actually less than 0. It is less than 0.05. Then we need to reject null hypothesis. So what does that mean, rejecting the null hypothesis? So what does that mean? We are actually saying we are actually saying that our sample, that is this sample, right? So our sample which is which was drawn from the previous universe, from the previous universe, the chance of getting this sample from that universe was very low. That is, what is it actually trying to say is, see here, what is it actually trying to say? Okay, so I've cleared everything. Now I'll explain what is mean by that. So here, what is it actually trying to say is, see, earlier we have observed that P is equal to 0.016, right? So which is nothing but P is less than 0.05. Then we are saying that we reject the null hypothesis. Why we are actually rejecting null hypothesis? Because if the P value is less than 0.05, then we can confidently say that this particular sample data, right? This particular sample data does not belong to this particular population, that is this particular universe. Okay, this sample data doesn't belong to this sample data doesn't belong to this particular population. That means this sample data belongs to some other data, some other universe here. So there is some kind of another universe here. So maybe this sample data belongs to this universe, maybe, right? So for that reason, we are actually rejecting this is not the right population for this sample, and this is the right population for this particular sample for this reason, right? And now when you look at another, when you look at another another thing here, for example, acceleration. When you look at acceleration, see here, what's happening for acceleration. See here, it is saying 0.918. So what is the p value here? 0.918. So this implies P is greater than 0.05, right? So if P is greater than 0.05, we don't have any kind of evidence, right? So we fail to reject we fail to reject null hypothesis, that is H naught. So that means we are actually saying that that there is no relationship between acceleration and MPG, right? So we are actually accepting the null hypothesis. That means we are actually accepting the null hypothesis. So what does this mean? So this means we are saying, I'll tell you. I'll tell you. So earlier we have observed that P is equal to 0. Maybe what is that P value? 0.918, right? So yeah, 0.918. So this is our P value. And when you plot the graph here between, okay, so when you plot the graph here, this is the acceleration variable, and this is the miles per gallon variable. When you plot the graph, what is happening here? It's saying the p value is actually greater than 0.05. So we accept, right? We accept. I mean, we should never say this term. So that's why I'm not using here. Why? Because in statistical term, we only use we have failed to reject. Okay, we failed to reject null hypothesis. That means we are accepting null hypothesis, right? So we are accepting null hypothesis. So what is the property of the null hypothesis here? What is the principle of null hypothesis? There would be no relation between x and y variables. So this is the property of the null hypothesis. So we are saying when you plot this null hypothesis on a scatter plot here, so you will be getting. So this is the mean of x here, that is x bar, and this is the mean of y here, that is the y bar. So when you plot the data here, so null hypothesis is true. That means there is no relationship here. So there is no relationship between the acceleration and the mpg here, right? So this particular sample, right? This particular sample is truly belonging to the population, right? So we can say that this particular sample is actually belonging to the population. So we can confidently say that, right? Okay. And now, so this is all. So this is all about this particular thing, that is the p-values here. So this is the thing for which p-values are very, very, very significant in analyzing. In the statistical analysis of OLS regression. Uh, and now you want to know about what is the t term here. What is meant by this particular t here, right? So I'll be explaining this thing. Okay. So okay, so I'll be explaining the T here. So remember one thing, that is this OLS regression results. This OLS regression results table is entirely based on T distribution. You should never ever forget this, right? So this entirely, the OLS regression results is entirely based on this T distribution. So what is mean by the T distribution? So T distribution is also similar to the normal distribution, centered which is centered at 0, right? So that is, it would be also the similar kind of, it would be having similar kind of a bell shape, and here the mean of this particular distribution would be 0 here, mean equal to 0. Okay, and it will be having some bell curve here. And when you want to know here, uh, for example, for a normal distribution, for a normal for a normal distribution, we say that z score, okay, z score equal to xi minus x bar by sigma, right? So this is the z score. This is the case here, that is the z score when it is about a normal distribution. But here this is the t distribution, right? So we usually say that t score, instead of saying z score, we will say t score, which is xi minus xi minus x bar by sigma here. So what is the mean here? The mean is nothing but the 0 here. See here, this is the 0. So you can say xi minus 0 by sigma. So what you will get? You will automatically get xi by sigma here. That is the value. But but when you look at here, so this will ultimately becomes t score equal to xi by sigma. So automatically, what is the value of xi here? Xi equal to t score into sigma here. So what is this xi here? This xi is nothing but the coefficient. Xi is coefficient. Xi is the coefficient, and uh, this what do you call this t score is nothing but the t. Okay, and this sigma is nothing but the standard deviation. So in specifically, I mean, in the short form, you can definitely have some kind of shortcut here for the formula. So you can call some coefficient is equal to standard error into t. So this is the formula here, right? So this is the formula for the uh, t distribution, right? So in the OLS regression results table, the tighter the distribution, that is, lesser the standard deviation and the better it is, right? So what is meant by the tighter distribution? The standard deviation should be less here. For example, I'll give you an example. See here. Okay, so for example, I'm having a straight line here. This is the x-axis here. Okay, on the x-axis here, this is for example, this is the 0. Okay, let's imagine here like this. Imagine that this is a 0, and here on the right side of my 0, I'm having the values which are, let's say, some 100, 200, 300, etc. And on the left hand side, I'm having minus 100, minus 200, minus 300, right? So when I ask you a question, what is the standard deviation here? So if I ask you this particular question, what do you say? So usually people will say the standard deviation here in this case is 100. Why? Because the difference between each data point, I mean, each unit of a x-axis is the 100 here, right? So the difference between 100 to 200 is 100. So that's why the standard deviation is 100, right? So just remember this particular thing here, and when I draw another, if I draw another kind of a axis here, and on this axis I have some 0, and then I have 1, 2, and 3, and 4 here. Now I have minus 1, minus 2, minus 3 here. So if I ask you a question, what is the standard deviation for this particular uh, axis? So what do you say? The standard deviation here is 1. Why? Because the difference between the 0 to 1 is 1, and the difference between 1 to 2 is 1, 1, 1. So you will say standard deviation equal to 1 here. But when you observe here, the standard deviation is 100. Here the standard deviation is 1. So which would do you think is the most stable one, stablest one? So which one do you think is the most better data? right? Which data is actually explaining more? I mean, which data is actually explaining better? See here, there is some kind of 100 data point. There is 100 units of a difference here, right? 100 units of a difference. So here the data is not explaining much. Okay, it's just skipping few more units. But when you look at here, there are not much difference. There is only one single unit of a difference here. There is no difference here, right? So when you plot them, see when you plot them on a graph like this, right? You plot them on a graph like this. Sorry. When you plot them on a graph like this, so you will get a data like this. So you will get a data like this, right? And now when you plot this kind of a graph, so what you will get? You will get a kind of a data like this. This would be your mean here, and all the values will become 0 at mean. And here the value would be 1, 2, and 3, and 4, and so on. Here the value would be -1, -2, -3, -4, and so on. But when you look at here, this would be the value that is 0, and here your values become 100 here. This is the 0 here. This is the 200 here. See, did you observe this thing? This is the 300. This is the -100, -200, and so on. See, the tighter the distribution, the standard deviation would be very less. If the standard deviation is very less, then we can say the distribution is tighter. It is having a tighter distribution. That means we can say it is a better kind of a data. It has the better distribution, better data, you can call it as. If the standard deviation is high, then you can say that distribution is distribution is loose here. So you can say that poor data. Okay, this data is not actually explaining much. You can say this is the thing. Okay. So just have a look at here. So just have a look at this particular coefficients here. So just observe here. Here we have all the coefficients, right? And just have a look at the p-values here. Whether if any p-value is greater than, I'll explain. If any p-value is greater than 0.05, so just spot out what are all the p-values that are greater than 0.05. That is 0.262 here, and this is 0.0, sorry, maybe, yeah, this one 0.918. Okay, so we have found that displacement and acceleration are the two columns that are actually having greater than 0.05. So what can we do here? So if p value is having 0.05, then what can we do? We accept I mean we fail to reject null hypothesis. That means we accept a null hypothesis. So what is the null hypothesis is stating? There is no relationship, no relation between x and y here, right? There is no relationship between x and y. So If x is, I mean, if displacement is not a good predictor to MPG, see, if displacement is not a good predictor to MPG, we have already known that by this hypothesis testing. And if acceleration is not a good predictor for MPG, then considering it in our machine learning model would be an absolute waste of time and uh, efficiency. So we won't be considering these two variables in our model here, right? Why? Because, and just observe the rest of the things here, the rest of the coefficient p values here. See here, the cylinder is having absolute zero value, and the horsepower is having absolute 0.016, which is less than uh, p here. And see, all the red lines are actually having the p values which are less than 0.05. What does that mean here? That means we are actually, we reject null hypothesis. We reject null hypothesis. That means we are saying that uh, cylinder, horsepower, weight, and year, and car type, these are all the variables that are actually a good predictors of MPG. This these are actually predicting much better. Okay, these are actually predicting much better our MPG column. MPG column. So we will consider this, right? So how to proceed for now? So we will drop the displacement and acceleration columns from our data frame, right? So we will drop this displacement and drop acceleration from our column, and we will create the data frame with the remaining variables, that is cylinder, horsepower, weight, and year, and car type. Okay, and then we will recreate the model again, linear regression model. The p values will again change those columns which have, see here, the p values which have very low values will now again change after when we create the model here, right? So that's the reason here. Earlier we have seen that these are having the very low value, right? Low p value are now, uh, I mean, when we create the model again, these low p values will become, may become high p values, right? So why is this happening here? So the reason here is the p values are actually changing. Why? Because is due to the reason of multicollinearity. So this is happening due to the reason of multicollinearity. So due to this reason, most statisticians, I mean, the sklearn library. Okay, due to this reason, sklearn won't rely on the p values here. So that's the reason why sklearn library is not actually providing all this table here, right? Why? Because why it is not actually providing all the tables here in the sklearn package? Why? Because they don't rely on p values due to the uh, due to the factor, due to the reason that this data is having multicollinearity. No matter whatever maybe the data is, that data will definitely have some kind of multicollinearity. Due to that reason, sklearn won't consider uh, these, I mean, relying upon these p values, right? Yeah. Okay. So yeah, this is the end of the thing here. So this is the explanation of all these contents in this table. I hope by this you have got the better understanding of the OLS regression results table. Now, if you ever see this table again here, hey, I have already just forgot to explain one thing. Yes, I have already explained theoretically, but here when you look at this standard error here, see this term standard error, this is nothing but the standard deviation. So by this you can decide whether the data is a tighter data or a bad data. See, if you look at here, intercept is having, sorry, cylinder is having 0.5. Okay, displacement is having 0.009. Okay, and horsepower is having 0.016, weight is having 0.01, acceleration is having 0.1, year is having 0.060, car type is having 1.041. So these are all the standard errors here. That's nothing but, what do you mean by the standard error means? You need to, 1 minute, just go here, and I have explained what is meant by standard error here. See, that's nothing but the standard deviation, right? So this is the standard error, nothing but the standard deviation here. That is the sigma, right? So this is the standard error, which is nothing but the standard deviation itself, and these are our significant coefficients. And this is the t value, nothing but pretty much similar to the z score, right? And this is the p value. So yeah, this is the thing here. So I hope you have got some better clarity regarding this OLS regression results. So how to study these results, you have, I hope you have got the good understanding by now. So I'll be explaining about multicollinearity and the scaling, the impact of the scaling on the linear regression, and some other shrinkage models like lasso and ridge regression tomorrow. Okay, so I'll see you tomorrow in the next video. I hope you have already enjoyed the session. Okay, so if you feel some kind of boredom here in this class, because I can understand that this video is a bit lengthier, so what you can do is you can just put the entire video in some 1.25x mode. You can play it. Just try to understand it. Why? Because I'm just teaching in this space. Why? Because this space would be an absolute one. Why? Because if you want to understand these complex parts here, see, for a newbie, for a fresher kind of person, this is not a small thing to understand. Why? Because these are all a kind of a jargon here. So by just, I mean, if I want to wrap it up things in a hurry manner, then I'm sure you won't be understanding all these things. So that's the reason why I'm explaining at this pace. Okay. So I hope you have understood. I'll see you in the next video. For now, good night. Take care. Jai Hind.